Hi there, Mr. Sutton here, bringing you this lesson on average value. In this one, we'll be calculating the average value of a function over an interval, and as a real-life application, we'll figure out the average monthly balance for an account. Now, when you saw the title of this lesson, you were probably excited because you're like, hey, I've been taking averages since middle school. I know everything about this topic. Okay then, in your own words, what is an average? Pause the video and see what you can write. Alright, so here's what we were looking for. An average, as we defined it when you were studying stuff back in middle school and earlier in high school, is going to be the sum of some items divided by the number of items. For example, if we have a map of all of LeBron James's playoff performances here, so a certain number of points in each of these different games he played, we would just add up all of his point values for all of these games and divide by the total number of games. And this would tell us his average points over this period. And this is easy enough for functions like this that are what we call discrete. There's only a specific number of items, and once you've gone through them, you're done. Like, we don't have to worry about a game 5.6, right? Or a game 10.7. It's just one game, 2 games, 3 games, whatever. Now, what if we have a different kind of function that we want to find the average of? A continuous function. So, for example, let's say that we took this chart and connected all the dots and made it represent something else like temperature in a city. How can we find the average value of a continuous function over an interval? And for temperature, I mean, it would make sense that we want to find the average in a different way, because otherwise, how are you averaging temperature together? Are you just taking the temperature at certain times of day and just averaging those? I mean, I guess you could just randomly test the temperature at times, but it seems like we'd be missing a lot of information if we didn't take all the temperatures over the course of this time period. So when you're doing average value for a continuous function, the sum of items in this case is going to be the area under the curve, the value of a definite integral. And this makes sense because whenever you need to add a whole bunch of things together, well, what is calculus's greatest adding machine? The definite integral. Okay, now how about the number of items? Well, this is a little bit trickier, but for this one, if you have an integral from a to b of f of x, the number of items, quote unquote, is really just the length of that interval. So that would just be 1 over b minus a. And 1 over because we're dividing by b minus a, right? And I guess we could write all of this over b minus a, but it just looks weird, so we make it a fraction out in front. So this is our average value formula for any continuous function. Now that we've gotten a look at the average value formula, let's take it for a test drive on this one. So we have the function 3x squared minus 6 over the interval 2 to 4, and we want to find this average value without a calculator. Pause the video and see if you can set up the integral to do this. Alright, so using our setup from before, we're going to have 1 over the interval length, so 1 over 4 minus 2, times the integral from 2 to 4 of whatever function you're trying to average. So f of x in this case, 3x squared minus 6. Don't forget the dx. And pause the video and see if you can finish this one out to find that average value. Alright, so we've got a 1/2 right here, and then I have the antiderivative of 3x squared minus 6, which is going to be, let's see here, this bumps up to a 3. Dividing by that, we've got x cubed minus 6x, all of this evaluated from 2 to 4. And when you're doing this, we're about to, expand this out with a 4 and a 2 plugged in. You have the option of distributing this 1/2 to both of those brackets of stuff, or you could just combine things and then multiply by the 1/2 at the end. I usually do the second of these approaches. So I'm going to have 1/2 and a big parentheses. Inside I've got all this stuff with 4 plugged in, minus all this stuff with 2 plugged in. So I have a 1/2, and this is going to be, let's see, 64 minus 24, which is 40. Over here we've got 8 minus 12, which is negative 4, but we're adding that, so plus 4. And then when all is said and done, 1/2 of 44 gives us an average value of 22. For this next example, we're going to find the average value of this f of x function over the interval from 2 to 4. This time we're allowed to use the Desmos calculator. So pause the video and give this one a shot.
All right, so if I'm allowed to use the calculator, I might as well put this f of x function into my Desmos. So let me just put that in there now. F of x equals, and then we have negative fraction 3 over x to the third. All right, so we'll come back to that. Now, what are we going to do with this? Well, using our average value formula, we have 1 over b minus a, so 1 over 4 minus 2, times the integral from 2 to 4, from a to b, of just the function that we're averaging, f of x. And we're not going to bother rewriting this. We'll just put in f of x dx because this is already defined. So let's go to Desmos and actually do all that. So new entry, and we'll just do 1 divided by, we can just do 4 minus 2 down there, and then integral int from 2 to 4, and we'll just put f of x dx in that integral, and instantly we get back negative 0.141 if we round that off. For this next problem, we're going to do another calculator-based average value problem, this time involving a trig function. And just for fun, we're going to throw in a real-life aspect to this and talk about units with average value, which can sometimes be a little tricky. So we have a bank account with a fluctuating balance in dollars given by this f of x function, and x is in units of months, where x equals 0 is the start of the year. We want to find the average monthly balance of the account for the following time period. So from negative pi over 4 to pi over 2. Weird time period, but hey, we'll go with it. So pause the video, and again, you can use the calculator on this one, and we'll round it to 2 decimals. Also, think about the units when you're doing this. All right, give it a shot. All right, so if I am going to do this on the calculator, again, I want to plug in my function. So f of x equals, and now we got 1,000 sine of x. Pretty simple function, although it looks kind of crazy if I don't zoom in at all. Well, one thing I'm also going to do here is, because these are just sort of weird x values I'm going to be plugging in, I'm going to create constants so that I don't have to keep rewriting these. So I'm going to let a equal negative pi over 4, and I'll let b equal pi over 2. Now I can just use a and b instead of having to rewrite this weird pi fraction every time. So what's my setup? I'm going to have 1 over b minus a. So in this case, 1 over pi over 2 minus negative pi over 4, or plus pi over 4, times the integral from negative pi over 4 to pi over 2 of my averaging function here, f of x dx. Going for that on Desmos, the way I can actually just write this in, I'm going to have 1 divided by, and this is, I can just write b minus a because I've stored those values. And now integral from a to b of f of x dx, and that comes out to about 300 point, they said 2 decimals, so 1, 1. Now, what are the actual units on this? To figure this out, we can do a little unit analysis. Let's keep track of the units that actually went into the forming of our expression here. So the b minus a piece down here, these were both x values. So those were both units of months. So we have months in the denominator here. In the numerator, we have the f of x and the dx units. F of x was our function that's giving us the dollars at any given time. And dx, the differentiable, that's all the months that we're multiplying by to get the total sum of all these profits and whatnot. So we've got dollar months inside here. The months from dx and the months from b minus a, those are going to cancel out, leaving us with only dollars for the final unit. Now, this actually happens every time you take an average value. The b minus a and the dx units always end up canceling because they're the same type of units. So you're always going to end up with an average value of a function. You're always going to have the same units as the original function.
We're going to do one more example, and as the title suggests, this is not the average problem. It's a little bit of a spin. Let's say f is a differentiable function such that f of 2 is 10 and f of 8 is 34. Based off of this information, find the average value of f prime on the interval from 2 to 8. Pause the video and see if you can figure out how to do this. All right, so for this one, you're basically given this f function, and you're trying to find the average value of f's rate of change. Well, if you want the average value of f's rate of change, then you just need the average rate of change of f. So in general, the average rate of change, the AROC of a function, is the same as the average value of its derivative. So this is how you can find average value of a derivative if they just give you information about the original. So the AROC in this case, that's going to be 34 minus 10, so f of 8 minus f of 2 over 8 minus 2. So 34 minus 10 over 8 minus 2. And if you wanted to, you could simplify that to 24 over 6. So there we go. At this point, we're going to talk about one specific application of the average value of a continuous function, and that is the MVT for integrals. Now, you might recall the MVT for functions, where we said if a function is differentiable, then there is some c value on that function such that f prime of c equals f of b minus f of a over b minus a. In other words, IROC equals AROC for the function. But it turns out there is a mean value theorem for integrals as well. So for this theorem, if f of x is continuous on the closed interval a to b, then there is a c on a to b such that f of c, the value of the function at this specific c value, equals 1 over b minus a times integral from a to b of f of x. In other words, the instantaneous value of the function equals the average value of the function over an interval. If a function is continuous on an interval, then at some x value on that interval, the y value has to equal the average value of the function. Kind of cool. At this point in the lesson, we're going to use everything we've learned about average value and mean value theorem of integrals to go back and prove the fundamental theorem of calculus that we just kind of intuitively went over in an earlier lesson. We didn't have what we needed to prove it back then, but we've got it now. If you're interested in this proof, then hang around and enjoy the ride. Otherwise, you can move on to the next thing in your life. So, let's say that big F of x equals the integral from a to x of f of t dt, where f is continuous on a to b. We want to find f prime of x. Now, we already saw, based on our fundamental theorem, that that's just going to be f of x, but now we're going to prove this seemingly straightforward, intuitive concept. So if we're taking a derivative, we can do that with the limit form of a derivative. So we can write f of x plus h minus f of x over h as limit as h approaches 0 is the same as this derivative that we're trying to take. Okay, well, what does the f function do? The f function does this. So f of x plus h is going to be the integral from a to x plus h of f of t dt, and then we're just subtracting this same stuff from that. Okay. Well, it sure would be nice if there was a way to actually subtract these up here. So let's see what's going on. This is actually one of our integral rules, but just to review what it looks like visually. Let's say we have some f of t function, and here's a on here somewhere. Here's an x. That gives us some area, which we'll call the integral from a to x of f of t. And then let's say that we have x plus h. It's a little bit more than x. This whole area is the integral from a to x plus h of f of t. Now, if we subtract these areas, which is exactly what we're doing up here, what do we end up with? Well, this stuff in here, this is the integral from just x to x plus h of f of t. So we can simplify all this stuff up here to what we have right here. Okay. And just to make this look a little bit less clunky, what if I move this h out in front by making it a 1 over h? Look familiar? So we have an integral from x to x plus h, and we're multiplying that by 1 over, well, I mean, in our limit definition, wasn't this stuff down here really just x plus h minus x, aka h? So, for those of you not taking the subtle hint, this is basically saying that f prime of x equals this expression that looks an awful lot like the average value of our function f of t. Now, since our interval is continuous here, that means, based on our mean value theorem for integrals, that there is a c between x and x plus h such that f of c equals the average value of our f function. This is just our mean value theorem for integrals. Now, since this stuff is equivalent to f prime of x, we can say f prime of x equals the limit as h approaches 0 of f of c. And we're going to go just a little bit further here. Since c is somewhere between x and h, that means that as h approaches 0, these two things getting closer together means that c must be squeezed into the value of x. So we can really just rewrite this as f prime of x equals f of x. Hey, it's the fundamental theorem of calculus. Hello again. So, hope you enjoyed the show. That's it for average value of functions. Till next time, this is Mr. Sutton signing off.